So once we have a signal that's been recorded, we need to start doing these corrections to get from the signal that's actually been measured at the satellite, at the sensor, to be something that looks like the signal that you might see if you were on the ground looking at the reflecting surface of the Earth. So there are many things that need to be looked at. We can break them down into different categories. So we'll start with radiometric correction. One of the things to look into here is the distance to the sun. So the strength of the signal that we're going to be seeing is going to be dependent on, for example, the distance to the sun, where we are in our orbit, which way the Earth is actually facing as well. So obviously we need to know precisely the time of day and the time of year that the image was taken, and whereabouts as our orbit changes through time, we also need to adjust for that. This will influence the amount of radiation, potential radiation that's coming in, how strongly the sun will illuminate the Earth's surface. And as we can see, the northern summer, we are actually quite a long way away from the Earth, from the sun. And so the summer in the north is not the same as the summer in the south, with stronger illumination there for them in the southern hemisphere. And even these positions aren't exactly so for the midsummer and midwinter. They're actually not at the extremes of the orbit, because why should it be that simple? That's the first model we need to have, the Earth going around the sun. We also need to know where on Earth we are. We need to georeference our image for very good reasons, several of them coming up soon. So we need to do this georeferencing to find out where we are. The Earth is passing underneath the satellite all the time, so we need to know which bit of the Earth has been imaged during an orbit going around the Earth, what's the rotation of the Earth underneath the satellite. And this will also influence, our position will also influence how much the light is spread across a surface of the land or the sea, if we're sensing that. It's very well known, I assume, that it's warmer towards the equator and colder towards the poles. A large part of this is due to the fact that the sun's rays have to cover a larger area. They come in, if we imagine that the sun is very, very far away and the light is traveling essentially in parallel lines, because of the curvature of the Earth's surface, we have this spreading out of the light up here. It has to cover a larger area in comparison to, say, hitting down here on the equator. No, there's the equator. So our light then is spread out. There's also the problem with a thicker atmosphere as well, which also comes into it. So we have this radiometric correction for the angle of the sun as we face it. How intense the light is as it reaches the surface of the Earth. And then we have the atmosphere. So light will travel from the sun, and we will have direct illumination. It passes through the atmosphere, but the rays of light coming from the sun, many of them will go straight towards a point on the surface of the Earth. Some of them will be going towards some other point on the surface of the Earth and then be refracted by the atmosphere towards that same particular point. They were heading down here and they were going to be the A line for this point, but instead they got refracted off and ended up hitting over here. Similarly, we will have some light from here has been refracted off to not hit this point. And then we have scattering within the atmosphere. Light that's just generally scattered, illuminating this point on the surface of the Earth, because we have molecules of gas in the atmosphere that interfere with the light. The light reacts with them and it scatters all over the place. So we get this scattering. And this is stronger in the blue than it is in the red, for example. And then the light travels back, doesn't travel back, sorry, it travels to the satellite. So it leaves, it's reflected from this point, light hitting here then may travel up towards our sensor. And similarly, light that was traveling along this path and was going to miss the sensor entirely gets refracted and ends up hitting the sensor. And we have light that is actually completely refracted at the top of the atmosphere or at some part of the atmosphere, never touches the surface of the Earth and hits the sensor. Other light will miss entirely. But this is the light that is being received at the sensor. So we have light that illuminates this point here, may be coming directly from the sun through the atmosphere, or it may have been light that was going somewhere else and then got refracted to this point, or we might even have scattering within here. Then we have light that leaves this point, goes straight to our sensor, light that may otherwise be refracted away from its original path and end up towards the sensor, and we have this entirely refracted portion here that contains no component of a signal from the Earth's surface. So all of these things will be in there, and luckily this should be our strongest signal, and these other parts are not as important, but we still need to consider that they are there. So how do we work with this? How do we account for atmospheric effects, perform atmospheric corrections? Well, ideally, we would like to use a radiative transfer equation, which is a model of the atmosphere. How is it working? Unfortunately, because variations in the atmosphere, temperature, humidity, and so on, will strongly influence how this model works, we can not often use it. We very rarely have enough data for the relevant location and time in order to be able to use this method. So instead we tend to revert to some sort of other method, calibration against a known target, for example. If we have a surface within our image that we know, and we know what it should look like, given the incoming radiation, given our model of what the sun is doing, and we know what it should look like, what does it look like? Okay, well we can calibrate our signal based on that. Unfortunately, again, these known targets or targets of known reflectance aren't that common. There are enough of them across the globe so that we can actually use them on occasion and calibrate instruments with them, but for individual scenes or individual images, usually not. So we can't really do that because we don't have anything within the image that is usable at that moment to compare with. So the last final fallback, and the one that is most common, is dark pixel subtraction, whereby we look for the darkest pixels in the image and assume that they are perhaps black, or assume them to have some minimum value. Water bodies, for example, tend to be very dark. So this is the more common, the least correct perhaps, but usually the one you're left with, just because that's how it is. So dark pixel subtraction. When it comes to thermal images, again we have the radiative transfer equation. We could try using that if we had access to the data. There's also the split window where, because when it comes to infrared, we have several bands of data that we're assuming correlate quite well, so we can construct a pseudo band, as it were, and with the help of that we can try to calibrate our image based on that, at least for the thermal infrared. Another way is the two-look technique, where we're looking at the same part of the Earth twice, but from different angles, and then the hope then is that the difference in the thickness of the atmosphere will not have changed for the thermal image at least. That should be more stable over time rather than the reflected light which will change due to incident angles and so on and so forth. But the thermal emitted radiation coming from the surface will be more stable, and then differences in the signal received will be entirely due to the atmosphere over that short time span that we've moved. So this sort of illustrates the point. And this we can do, as I said, with the thermal infrared because it's a more stable signal. It's the light is emitted by this surface. It's not actually reflected. Some of it will be reflected, perhaps, but we're essentially saying that the strongest part of this signal is going to be the emitted part from the surface of the Earth passing through the atmosphere.